All right. Good evening, everybody. Pick up where we left off last time. For those that watched last video, we were talking about choosing new resistor values to go around the PMIC in our project here, the BQ24074RGT. And I dug in, looked at a bunch of, got those all sorted out for which resistors do what. And I've actually started working on, let me actually open that up. There's some documents. Okay. This is a mess right now, but I'll clean it up eventually because I think it would be helpful to other people that use this chip in particular to help them choose values. And so right here is kind of really where we're going to focus. So I grabbed some of the constants out of the data sheet, like this K for current limit, for current set, for timer. These are the constants. These are just straight out of the data sheet for the PMIC. And then here are the values that we can set. This R current limit, R current set, R current termination, R timer. And then here are all the different things that are affected by that. And so right now, these are the values that we have in the these are not actually, I changed this. Let me change this back to what it is. This is a 4.99K. And that's just, again, if you look at limit, set, and term, we come over to here. It's just these values. Here's set. This is limit, not timer, not term, timer, 71.5. And then term is 1.5. And so these are all in ohms, not kilo ohms. So you have to actually take them out to the thousands. And then you can see if I move this just a little bit like this, there's a couple of different things that all of these control, and that is wrong. I've got one of these not right because I've done something weird. Oh, this is 2200. 2200. And it's the set, I believe. Yeah, it's the set that's 49. There we go. Enter. Okay, and you can see the in current limit. So this is as much current as the PMIC will consume to both run the device as well as charge the battery. So this is sort of your like total bucket of current that you have, regardless. Like if your charger can supply an amp or 2 amps, it doesn't matter because of how I've chosen these currently, that is, it's only ever going to consume 730, about 2 milliamps of current total. Again, to run all the electronics that are on this board here, as well as charge the battery when it's plugged in. And then the fast charge, if you remember, that is the amount of current used to charge the battery while it's in that linear charging zone. And so that's going to be just about 180 milliamps. The time for pre-charge, and the pre-charge is only used when the battery is below a certain threshold, like really dead, and before it hits it with that fast charge current and put it on the linear slope, it'll do a pre-charge current, which down here you can see is about 17 or 18 milliamps. And it will do that for this many seconds. And I can actually do, I was doing things like changing that to hours. So that many seconds, there's 3,600 seconds in an hour. So that's almost an hour that it would stay in pre-charge. And then this T-charge is set by the timer resistor to say this is the maximum amount of time that it will charge before it turns off. And that turns out to be about 9.5 hours. For some reason, I thought it was 6, but there you go, 9.5. And then the termination current, which is about 9 milliamps. And that's, again, in the data sheet, after it's gone through that phase and got the battery topped off, it like drops off down gradually down to 9 milliamps. And once it hits 9 milliamps, it just turns off. And so what we can do now is, like I was saying, we want to have a more fast charge current for the new battery because 180 milliamp hours is going to take 10 hours to charge our new battery, and that's too long. and we don't need to be as thermally conscious. And so what we're going to do is, just as an example, if we changed our set down to 2200, you can see now we'll charge with 400 milliamps, about 405. We still only have 730 to deal with, which isn't quite enough. And I'll talk about that more in a minute. But if we're using 400 and, just say 400, round it down, 400 milliamps to charge the battery, that only leaves us 330 milliamps for the electronics, which is fine when it's asleep. It won't matter. But if it's running Wi-Fi or anything, and this thing can get up and draw, have a spike in like the 400 or 500, it's going to clip past this current limit. And so we might want to set the limit a little higher by changing the I limit resistor. Let's say if we just change to 1500, I think lowering it raises the current limit. Yeah, see, now the current limit's way up, like an amp. The fast charge stays the same, and then so anyway, I created this little thing, and I'll tidy it up, and I'll probably post it so other people could use it, where you can just play with different common resistor values and see how it affects your current limit, your fast charge, your pre-charge times, and all that. And that way you're not doing all this math over and over. And so that's what I was working on. But then I'm going to change these back. Excuse me. Got the burps. 49. Okay. So this is the current configuration that we have. And what I realized is that, yes, while I just realized my sound might be messed up. Let me check my sound. Stand by. Sorry. Just want to make sure I'm on the right output. Yes, we are. Okay, good. Sound should be good. What I realized is that USB has certain limits, and this is came across this in the data sheet for the PMIC because it reminded me that USB, the standard, has certain current limitations. And so on a USB 2.0 port, you are limited to, they call them, what do they call them? Load units. And the 100 milliamps is the initial max of a USB device. You plug it into a USB 2.0 port, you can't draw more than 100 milliamps. Now, you can if the device requests it from the host. So when you plug in a device into a USB 2.0 port that needs more than 100 milliamps of current to work, it will talk to the USB host and say, hey, 100 is not enough. I need up to 500 is the max. And so you can request up to 500 milliamps. And the host will give you that. But there's a negotiation there that has to happen with the host, and so a logic chip has to handle that. You can't just start drawing more current. And the USB standard says on a self-powered hub, like I use here on my desk, you can't see it. You should never draw more than 100, regardless. Like, even though you can ask for up to 500, you should never draw more than 100, because it doesn't. A hub has a bunch of different ports on it. It's requesting a certain limit from the host, which in this case is my computer, a laptop or a tower or whatever it may be. If you have 5 ports and each of them wants to request 500 milliamps, now you're at 2.5 amps, and the one hub connection just can't do it. Like, you can only source so much. Like, there's current limits in everything, in your host and your laptop and in the hub and things like that. And so which is weird because I have been using this hub and I know I've been drawing more than 100 milliamps. And so I am not sure. I used to be, in fact, where is it? What's that? Like, credential flash here. I have read this book, USB Complete 4th edition. Like, when I first was doing PIC microcontrollers, like, I was super into USB devices and writing code for that, and I really knew all of the details about the power management, but this was years ago, like almost 10 years ago. But I thought that the host limited the current. So when it says, 100 milliamps is the limit, I would have expected it to, when I plug in my device, to limit me to 100 milliamps. And so, but it's not. And the reason I know it's not is because I'm going to change the view. Stand by. Here we go. I apologize for this display here. Like, it looks perfect to me, but the way it's backlit, it's awful for the camera. So, what we have here, down here, this is the one that we're going to focus on, is just a little USB current tester. You can plug it in, then you can plug in a device, and it'll tell you how much current that device is drawing. And when I've plugged this into, have I plugged it into the hub? That's a good question. I think what it does is it requests the 500. Like, it does the negotiation to say, hey, I need 500 because I have drawn more than 100 through that thing when connected to a hub, I think. But the whole point of all of that is that I was really sure that all we needed to do was pick some new resistor values, but then I started realizing, what are we doing when this is plugged into somebody's computer through a USB port? And not to charge, because as I was going through the calculations, you're not going to charge that way because of the current limit. Like, you're just not going to get enough juice to charge the battery. And so, and I haven't been suggesting to customers to charge it that way. I always suggest they use a USB charger, like their phone charger, which those have 1-2 amp limits on them. And so that's okay. But what I started to worry about was, when you connect it to maybe configure it, are we doing the right thing power wise? Because we're not asking. What I would expect is that the device would never get more than 100 milliamps, because I have nothing on board this device. And I should just put it down here in the camera. Nothing on this device right here that negotiates that higher current limit. It's not going to ask for more than 100 milliamps. And in fact, let me get a pointer here. Okay, so right here, this chip right here, this little black square, that is the FT230XQ? What is it? I think that's right. It's an FTDI chip that does USB to TTL. So this chip right here takes input from the USB and turns it into just serial ones and zeros to go to the ESP32. And so this, when you plug it into a computer, is going to register this entire device as a USB device. It'll actually show up as a virtual COM port for those that are familiar with that. But by default, and I learned this from the data sheet for the FTDI chip, by default, it's only going to request, I believe it's like 98 milliamp. Like, it's not even going to request, which doesn't make sense because you have to request them in unit loads, so in 100 milliamp increments. So that's weird, but the data sheet definitely says something less than 100. It's like 90 something milliamps is what it requests by default. And so that's definitely not going to be enough to hardly do anything. Definitely not to turn the Wi-Fi on the device. However, again, I've had this plugged in. It connects just fine to Wi-Fi. I've had other dev boards that do the same thing. They connect just fine. And so something's not adding up, and I don't know. And I hate when there's a information gap there. Like, I could just say, well, it works, but I don't know why it works, and that scares me. And I don't like being in that position where it's like, well, it's been working all this time, but then when I go back and I read through and do all the math, it's like, how is this working? I don't know, which is a pretty common theme in programming to begin with. But so what I'm hoping to accomplish today, and I do not know how far we're going to get on this, is I used this device here to determine that the charge circuitry was working correctly on our original hardware, making sure that this fast charge current is right around 180, 178. And when I plugged this in yesterday to test it, I was getting a number on here that I didn't expect. And then when I plugged the new hardware in, I was getting a completely different number that I didn't expect. And so that bothers me. Like the numbers, I should get the numbers that I expect. And if I get different numbers, I need to know exactly why I'm getting different numbers. And so where we're going to start today is I have used this fancy Tenergy TB6B, which I recommend as a tool for it. You can charge batteries, discharge batteries. It'll show you how many, like the capacity as you're charging it. It'll show you how much capacity it was able to put into it. And on the discharge cycle, it'll tell you how much capacity it went through. It's really a fancy piece of equipment, not very expensive. I want to say it was like 50 or 60 bucks. Like it wasn't too bad. And so I have used that to discharge this battery. I got a camera 1, camera 2 thing here. This battery down to below where it should be in the top off phase, above the pre-charge phase. So we should not be in the pre-charge current like this 17 or 18 milliamps. And we definitely shouldn't be in the, when it's in the, let me bring the data sheet back up. Let me bring it over here. And we'll find that graph that we were looking at yesterday. So you can follow along. Come on, where are we? Almost there. Right here. Great. So again, if you're below a certain low voltage threshold right here, oh, you cannot see that. Let's switch over. When you're below this low voltage threshold, you're going to be getting I pre-charge. So that's that like 17 milliamps. And that'll get it up to right around here to above the low voltage threshold. At that point, you're going to get fast charge current. That's that 180 milliamps. And then as soon as the battery gets, filled up, it maintains a constant voltage, but then lowers the current to top it off. So it keeps that voltage up at 4.2 volts, I believe it is. And then the current tapers off to top the battery off so you're fully charged. And so if you're in this zone over here, you can get any value of current between fast charge current and termination current. So it could be 20, 30, 40, 50, 60, 130, like somewhere between 17 and 180. And so what I needed is a battery that's in this range, and I'm going to plug it in. We're going to go back to the overhead view. I'm going to plug it in and see what charge current I get on the old hardware and then compare it to the new hardware, because there are differences, and we'll talk about those as we see them. But let's do this test. And so right off the bat, what should happen, by the way, is this device right here is going to connect to the internet, connect to the Wi-Fi, reach out to the internet, and get stats. And then as soon as it gets stats, while it's plugged into power, it's going to wait, I believe, 20 seconds, and then it's going to go into a deep sleep mode. And so I have other tools that will give a more accurate current consumption that you can follow very closely. But for this is sort of a very cheap, blunt tool to get the same information when the current's not changing very often, if that makes sense. And so you can see right now I have this connected to a charger. This is not connected to a laptop. I won't have any current limitations in that regard. You can see that it's sitting at 5.22 volts, 0 amps. And so what we're going to do is we're just going to plug this guy in, maybe. Plug him in. Okay, little flash. You're going to see the current, 180 milliamps. It updated, 180 milliamps. And so it's sitting at 180 milliamps right now, and then it should go to sleep. And even if it's not asleep right now, it might just not be using very much power. And so, and I'm trying to think, let's just we'll let it go for a minute here. Okay, now it's down to 0. Great. Yes. Okay. Sorry. I don't have a battery connected. That's exactly what I would expected. So it did its thing. It was around 180 milliamps, just so coincidentally, just happens to be the same as our charge current. But the battery is right here. It's not connected. And so now what we're going to do is we're going to disconnect it. We're going to plug in the battery like that. Now it's going to update again, and we're going to let it do that. And then it's going to go to sleep immediately. When the hardware detects that no external power source is connected, as soon as it's done updating, it goes back to sleep immediately. It's awake for as little as possible for maximizing battery life. Okay, so great, exactly what we expected. And obviously this is still at 0 because it's not connected, it's right here. So now what we're gonna do is we're gonna connect it. And you see now we're up to 360 twice, because remember we were at 180 before. It's gonna update, we're still at 360, and now that makes sense. 180 milliamps is going into the battery, just as we would expect, and 180 milliamps is going into keeping the Wi-Fi on. It's checking a bunch of things, and then it'll go to sleep here in a minute, and that should drop back down to 180 milliamps. So let's watch it right there. Perfect. You see that? Let me point with my pointer here. 180 milliamps. So perfect. That's exactly what I would expect. I'm getting 180 milliamps. Now, if I were to watch this for hours or whatever, it would eventually start tapering down. It'll get to that 9 milliamps at termination, and then it'll cut right off. So great. That is working exactly as I would expect. Perfect. Great. We're going to disconnect and disconnect. So, shocker, the original hardware that I've tested thoroughly and have shipped to customers is working as I would expect. Now, this guy is where we've been running into some problems. And so what I'm going to do is we're going to switch screens again. Back over to here. We're going to launch Arduino. The charge circuitry on this, let's do it like that, flip it up. Flipping it up is better for the light. The charge circuitry on that, the PMIC, same, resistors around the PMIC, the same. It's this right here, which is exactly what's in the production hardware currently. And so, but I feel like I'm seeing different results, and it might have just been the batteries I was using. So we're going to verify that. We're going to open a recent sketch, which it might be a little hard to read, but okay, what we're going to do is we're not going to, I was just testing that it worked. We're going to comment this all out. And what we're going to do is we're going to put it to sleep. And I don't know exactly how to do that in the Arduino. Arduino ESP32. Bring this over so you can follow along. Docs. Yeah, like where? Let's just go down here. There we go. Decoding. Using platform IO. I want to put it to sleep. Just like I am on my existing hardware. Like I want it to let's just do Arduino ESP32 sleep. Random nerd tutorials. I write all my production stuff in ESP IDF, so I don't use the Arduino IDE for my stuff. So let's look at this. Here we go, deep sleep. We're looking at 150 microamps, so like nothing. 5 microamp. Yeah, that's really great. It's really, really great. So how do we just call ESP deep sleep start? I mean, let's just Let's copy pasta. Let's do it. Right here in the setup. Just put it right to sleep. See if that... I don't think that's going to compile. Is that going to compile? Not if you don't put a semicolon at the end of the sentence, dummy. Sweet. It is going to compile. Okay, I feel like there's maybe more we should know about that. Enable timer wake up. I don't really think I care about waking it up right now. Yeah, and wake up reason. This is all super interesting. Then after all the tasks, ESP goes to calling deep sleep. Yeah, so what we're going to do, just to be able to catch it, inside of our setup here, we're just going to call a delay 10 seconds, like that. All right, let's program this guy. Oh man, the ESP32 program's so much faster than the ESP8266. Not even close. Okay, that's it. It's done. Programmed. All right, now let's switch our view again. Yeah. Okay, let's get this guy out of the way for now. And what do we want to test first? Well, let's just test the... Let's just plug it in. So we're seeing 20 milliamps. 4, 5, 6, 7, 8, 9, 10. Look at that. It's so low that it's not even registering. Went to sleep. Okay. So it uses 20 milliamps. It uses 20 milliamps, and in deep sleep, like not even registering, as the other one wouldn't have either. So cool. Now, let's just unplug. Plug the battery in. Oh, I plugged it in too far. Dang it. It's going to be hard to get out. All right. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi. I'm worried about this. 8, 9, 10. Was it 20 or was it 2? But so it's definitely asleep now. And look at that. I'm right at 180. So what I saw yesterday was probably a combination of me staying up too late and having the battery in a weird state of charge. Interesting. Okay. So that's right. That's what we'd expect. 180 milliamps. Great. I am curious though. Take that out. Let's take the battery out. Was this? Yeah, it was 0.02, which would be 20 milliamps. 20 milliamps. And then it'll drop down to 0. So I guess I would have expected to see 182? 182 and then drop it down to 180? But regardless, when it was asleep, it was juicing the battery with 180 milliamps. Let's just do it one more time. Make sure we're doing this right. So that looks good. Looking real good. Here we go, 220. This is what I was seeing. Now it's down to 180. 220, yeah. I hope you were paying attention there. That went up to 0.22, which is 220 milliamps. That's what I was seeing yesterday. It was going up to 220 milliamps. And I couldn't explain that. That's a big difference. That's an extra 40 milliamps. And I know that this guy right here, the FTDI chip, consumes about 8 to 9 milliamps when it's active. It won't be active in this configuration because it's not negotiating with a host. There's no data lines connected inside of this cable right here. It's just a straight power connection. But interesting. I'm gonna hit the reset button. Let's just watch it again. See what happens. Reset. Goes up to 220. So I'm using 40 milliamps to do something. 40 milliamps. And then I appropriately drop down to 180. So it's still doing the correct charge current. That's good. But where's that 40 amp coming from? 40 milliamps. Wow. Take the battery out. Let's just go straight. This guy. $20. So at most, I would expect to see 200. And then now that it's asleep, let's button. 20 milliamps. So somewhere in there, when the battery is charging, getting up to 40 milliamps. I don't like that. I don't know why that's happening. But the charge current's right, so that's good. That's good news. .2. What happens if I just hold it and reset? And now it's dropped down to 0. So now it boots up. Okay, well. Okay. So, what did we learn? The charge current's correct. I'm missing 20 milliamps. I've lost 20 milliamps somewhere. And versus charging the battery and not, why would that be this thing? Where would that current be going? Now, I did want to look at, let's come back over to our data sheet here. And let's look at the current that it consumes just to do its job. Input, output current, well, that's the continuous. What it can use. I wonder if this is what's getting me. This charge and P good. So if you look, charge and P good are pulled up to 3.3 volts. And when they're charging, they're pulled down, but that shouldn't V over R. 3.3 divided by 100K is like crazy. I don't think we're losing it there. Divided by 100,000. We're talking microamps of bleeding current there. So it's not that. Interesting. Okay, let's just keep going through the data sheet here a little bit more. But these are going to consume some amount of current based on the state of charge and things like that. Operating voltage, current. Electrical characteristics. Here we go. Current source checked during startup is 1.3 milliamps, so that's not much. Active supply current. Okay. So 1.5 milliamps. So, I mean, we're getting 1 or 2 milliamps there while it's plugged in. So it's not that. Okay, well, I was hoping that maybe we had lost source current for bat pin short circuit detection. 7.5 milliamps. Guess it could check that. I guess my biggest concern is that I don't see it on the production puck hardware. I'm only seeing it on the redesigned stuff. Okay, well, we're going to move on. Yeah. Okay. Sorry, I've been referencing things in the data sheet and just realized that you can't see that. This is what I'm looking at right now. We got 7.5 milliamps for battery pin short circuit detection, but that should be for just a second. And the other one I was looking at was where? The current source, 1.3 milliamps right here. And the quiescent current, like that it's using active supply current. So when it's active, it looks like it uses about a 1.5 milliamps of current. So, all right, that 20 is just going to be a mystery for now, I think. It is sourcing the correct amount when it's in deep sleep mode. So that circuitry is correct. We'll figure out and mess around with where that other, and it could just be, honestly, it could be a state where, I mean, we're not, this is not a lot of code, right? Like we could be missing turning something off. There could be a race condition that's not handled in the Arduino code. Like there's a lot of reasons why we could just be missing 20 milliamps, but okay, well, we'll come back to that. Okay, we're gonna call that good. Like I feel good about where the charge current is. And then changing the resistors. So that's what we were working on last time. I don't want to do yet because I went back and I read the old data sheet for these batteries, the smaller ones. And the termination current, let's go back to the spreadsheet here. Can we zoom a little more so you can see that a little better? The fast charge for the new battery, I know I probably want somewhere around 400. And so I think if we are set this down to 2200, that'll get us up to 400. At 400, that's going to charge the battery in about 4.5 hours, and I think that's pretty acceptable. We'd want this current limit to go up, and so ILM 220. Something that you should consider is when you're looking at your bill of materials. So if you see this 4.99K, let's go into our list here. This is actually pretty interesting and something I learned going through this the first round. R, where are my R's? Here they are. R1, 4.99K, and if we can make this bigger, can we make this big enough to see? The quantity, if you follow this across, the quantity is behind my head. Let's lift it up here. 4.99K, you come all the way over, 1. So I have that resistor is a unique part that I have to pick a part number for, give it like this right here, this part number right here. Like I have to come up with that and make sure that it's stocked and follow the stock. So the more unique parts you have in your bill of materials, the harder it is to maintain that bill of materials because, again, you have to have you're tracking end of life for extra components and making sure that everything is in stock and supplied and all that. And so if you can reuse components, it's way better. So if you need, for example, a 9K resistor and you're already putting like 10K, you can see here. Maybe you can't see here. It's below my head again. Come on. There we go. This guy right here, there's 6 of these. And so if I have a 9K and I can get away with a 10K, I should just change it to a 10K so that I can have a lower part count on my bill of materials. So that's something that I figured out the first round through, that it gets hard to manage these bills of material when you've got all these different resistor values. And I did a video a while back where resistors and capacitors come in and out of stock right now, capacitors especially. The supply, the global supply of those is very short, and so you have to change those part numbers like every run that you do. And so the less parts that you have to do that for, the better and the faster you get. So changing that 4.99, let's go back to our chart here. If I change it to a 2200, I know I've got another 2200, and that gives me 400 milliamps. Now, if I wanted this to be 500 milliamps for my fast charge, I can come up with a resistor that works for that, but then it's a unique extra part. It's not going to be one of any of the other resistors I have. And so that's kind of a, I'm going to call it a pro tip, a tip that I've found, that if you can use resistors values that you already have in your bill of materials, that is good. And so for termination, I want to leave that the same. So that's 20 milliamp. That's probably okay. The termination current, I need to check the data sheet for, because it specifies what it should be, and I can't get the data sheet until Chinese New Year is over, and so I can't choose all these values until I get the data sheet. But I know the fast charge, I want it to be probably around 400, so I'm probably looking at a 2.2K resistor there, and then on the I set, and then for the, what was the other? Oh, the current limit, ILIM. I want to drop this, so let's go with 1500 and see what that changes us to, because I already have a 1500. Again, keeping the part count low. That gives me an amp. Current limit, just over an amp, and I think that's fine. So that gives me 600 milliamps to run the ESP32. It probably doesn't need to be that high, honestly. Let me look at the bill of materials and see what else we got in here. The bomb. We've got a 1.5, we got a 2.2. A point, yeah, that's it. We're out of luck. So we'd have to get another unique value. So either use a 2.2 and set it at 1 amp, or okay. I'll have to think through that. We'll do that another time. Okay, let's look. Let's actually make sure that we're not erroring out. Just quickly check my pucks, make sure they're doing okay. Okay, what's next on the to-do list? We've already done that. Oh, battery level detection. Oh, okay. I don't know if we've got enough time to do that today. Let's talk a little bit about the PMIC some more. Okay. You connect the battery, and you've got an input supply. This in comes from the USB, micro USB port. And again, this chip is responsible for deciding which of these to use to power the load. It will favor the input up here over the battery while the input is connected so that it can charge the battery. Now, you've got 2 output signals here, this P good and the charge. And I talked a little bit about those before, but the charge goes low when the battery is being charged. So when the PMIC is charging, it will pull this line low. Otherwise, you can see it's pulled up to 3.3 volts through a 100K resistor. But when it's charging, this will pull it low. And so I have this this charge connected to the ESP32. And so I can use that to say basically a binary. Is the battery charging or not? And that's the extent that I have on knowing the state of the battery, charging or not. P good will be pulled low. Again, you can see it's default pulled high through 100K resistor up to 3.3 volts. When it detects a valid source on the input right here, it will pull P good low. So plug in a USB cable that's connected to a valid power source where you're getting 5 volts. It will pull that low. And so this lets me know, is external power connected to my ESP32? And is the battery charging? Because you could, now charge can never be low without P good, but P good could be low and charge could be high because the battery is already fully charged and it's not charging. What I lack, and I've debated about this, and I wish I had more people around to give their feedback, but right now I'm talking into the void. What I lack is the ability to know how much battery life we have left. So it would be nice to say, hey, the battery's getting low, it's time to charge. And originally, the way that I had planned to implement this was extremely, I'm going to call it creative. I was about to say hacky, but I'm going to say creative. Is when the battery gets low, the device is going to brown out. It's going to bleh. And when it does that, it'll boot back up. And when it boots back up, a lot of times you'll have enough juice to get it. Like you're teetering on the edge, it browns out, it comes back online, and then you're still online for a little bit. And it normally doesn't go brown out and then never come back on ever again. And so my creative way, given the hardware that I have to work with, was the ESP32 has a code when it boots up that would tell me, like, the reason I reset was somebody pushed the reset button, somebody reset in code, it crashed. Like, it has a reason code for the reset, and one of those is that I browned out. And so I could use that to say, oh, your battery's low. You browned out, your battery's low. But I keep wanting to say creative. It really is kind of a hack. I think it's a creative hack. Like, it is a way, again, without any additional circuitry, to determine or figure out that your battery is low. Now, I hate it. Like, I don't love that as a solution. And there's a couple of other solutions that we could pursue. And that is one of the things I also want to decide on as we're doing this hardware redesign. And let me talk through each of those briefly. You have what's called a battery charge monitor, which essentially keeps track of the coulombs, I believe it is, that are coming in and out of the battery. It's a whole separate chip, and its job is to determine the energy essentially that's going into the battery and coming out of the battery to give you an idea of, it's a fuel gauge. That's what a lot of the parts will call it, a battery fuel gauge, LiPo battery fuel gauge. That is going to require an increase in my bill of materials. I have to have an extra chip. I have to have, I think a lot of them don't require a lot of supporting circuitry, but at minimum, an extra probably resistor and capacitor here and there that I'm gonna have to throw around that, as well as code. The ones that I've looked at so far mostly work on I2C. And so I would have to not there. Back up here on the ESP32, I would need to connect to the I2C lines a whole separate chip that I would read from. Now, super cool. Wouldn't be I say wouldn't be a lot. It would probably add like over $1 to the bill of materials just to get a battery reading. And it's kind of expensive. It's really slick, and it's a great, it'd be a cool thing to have, but I think that's a little expensive. The other thing that we could do, that I've been researching, is straight up take the battery voltage right off the battery which is in the power block here. Right from here, yeah, because we not even this three. This is a regulated 3.3 volts that comes out and powers. Um, I'm saying take the battery straight off of pin 2 here. Let's zoom in, like right here, and feed that into an analog to digital converter pin, an ADC pin on the ESP32 to get a reading. The problem with that is what? Tell me what the problem with that is. The battery is the battery voltage is non-linear. So on a lipo like this, fully charged is going to be at 4.2 volts. Fully discharged, it will go down to, I believe, 3 volts or 3.2 volts. But it's not this beautiful, I'll come over here for you, like this beautiful curve down of like as it drains, it does that. It's sort of, let me see, kind of comes like this and then drops off. And so you'd have to account for that in any sort of logic that was just doing a straight analog to digital read. And as I've talked to myself just now talking through it, like, why wouldn't I? Oh, okay. See, I was about to say, why wouldn't I do this? Why wouldn't I just plug it into an ADC pin and call it? The other thing that I'm a little worried about is the current that it will require. But if we use high enough resistors, the current draw for that should be in the microamps, should be negligible. And then we'll just always have the battery voltage. We would divide it, right? So the battery can go up to 4.2 volts. The ESP is running at 3.3. And the swing on the ADC, I believe, is up to 3.6 volts. But reading through forums, it's not great. And so what you do is it works best if you can get the range down within 1.1 volt. So if you can get the 4.2 translated down to 1.1 volt so that that's fully charged, like when the ADC reads 1.1 volt is fully charged, and then as it dies off, you read lower and lower values. Maybe I should just play with that. Can I do that on this? Let's look. I broke out the pins on this, if you remember, like this little header up here. I think, like specifically, I broke out the ADC. Like I think I did that on purpose. Right here. Here is our connector, our 10 pin. So I broke out those, and then let's just find the data sheet for what those pins are on the ESP32 room module. Because even if it's not perfect, like because it's nonlinear, even if it's not perfect and I can get an ADC reading and just know like, hey, when it's about this, like the battery's getting low and you should charge it, I think that would be helpful. Not just as an indication to a user, but also I could send that data to me to just kind of keep an eye on batteries and know like if somebody's device goes offline and then they call in from support, I can say like, oh, hey, it looks like your last known battery voltage was low, just as like a helpful support thing. So let me, this is a 27-page data sheet. I don't know that this is the one that we're looking for. I'm bringing it over here, so I'm not keeping you in the dark. Okay. IO pins. I need to know what they do. Okay, great. Here we go. Let's throw you over here. And let's move you right over here. I'm starting to get window overload here. Okay. We can just, there we go. Okay, great. So IO looks like we start at 22. IO 22 is nothing in particular, just an IO. IO 25 is an ADC right there. So that's great. I can use that. IO 26 is also an ADC. Channel 9, IO, what was next? 32 and 33. 32 and 33. Oh, that's right. I also specifically chose RTC GPIOs. And this is ADC1, channel 4 and 5, and ADC2, channel 8 and 9. Okay, so I've got all sorts of access to ADCs on that. So the next part of that is, where's the best place to grab the battery voltage? Oh, what am I talking about? Where's the best place? Right here. Sorry, let me switch the view. Okay, so to test this theory, what we could do, bring this up a little bit. Sorry, the lighting's kind of crappy. This is the battery right here, and this outside pin is the positive. The inside pin is the, do I have that right? Yeah, negative. And so I could actually just take, I could solder a little wire from right here. That'll give me the battery voltage. And I need it to voltage divide. So I could just bridge that off into like a little breadboard, divide it down, and then come back into just one of the pins up here, and then read that through firmware. Let's do it. Let's see if we can do that really quick. Because if it's that simple to get a voltage, and we'll see how much we can actually measure how much current it uses. And if it's that simple, what we can do is we'll just add it. We'll add it and we'll pipe it into one of the ADC channels, and we'll use it or not use it. Like, again, this is an example of where if it doesn't cost anything, and in this case, I'm talking 2 resistors, I just have to do a voltage divider, and that's going to be cents. And if I can get the current, which I believe there's no reason that I can't just use higher resistor values, and then the quiescent current on that will be negligible. So if there's no negative side effect to doing that, even if you're not going to use it in firmware, it's a good idea to put it into the hardware, because then utilizing it is just a matter of a firmware update. And so I could put this into the firmware and then decide, into the hardware, excuse me, and then not use it at all. And then, 3 or 4 iterations, firmware updates down the road after I've done a bunch of other things. If I say, oh, hey, now it's time to add the battery level feature, it's just a firmware change at that point. I don't have to worry about doing another run of hardware and testing or anything. It's all built in. So highly recommend, and I did this with a few other things that, excuse me, it's a good idea to place them in the hardware if you can. And even if you're not sure, you can do things like, let me show this. I think it's not what, here we go. This is great. This is the original hardware. Let me see if I can just get a little bit more light on this. Don't fall off. There we go. A little bit. I don't know how well you're going to be able to see that. Let's turn on. Let's get the real light going here. Let's see what this does. Got this on a. Ooh, that's bright. All right. Okay, so this is the original hardware with the P1, but right here, I don't know how well you can see that. It's looks like a Y-wing if you're a Star Wars fan. It's got like the 2 legs right here and here, and then the nose right there. I'm gonna try and pull it in close. I don't think it's gonna autofocus correctly. I'm gonna hold it right there. This thing right here. It's not placed. It's a pad and a footprint for a component that was never placed. And so you can even do things like that where it's like, I'm not sure, just put the footprint in the design and then add it later. And you can do the same thing with like little jumper pads. You can just have two little solder pads right next to each other that aren't connected. And then if you want to enable that feature, you just put a little blob of solder across it, like hugely helpful. And it saves you from having to send another board off to be fabbed and assembled. And so another tip, if you like, put as much into the hardware as you can without compromising the design and in my case, power consumption is huge. Like I could put a bunch of things on here, but it's gonna kill me power wise. But include those things in the hardware and use actual physical jumpers or placement things to activate or deactivate those features. It'll save you some time and it will save you money. And so, okay, sorry, that was a sidetrack. I feel like that's valuable for people to know and understand. So if we can put that in, we should do that. And so let's figure it out. Let's just do I got Windows, like on Windows here. Let's get rid of this one. And we can get rid of this data sheet. No, let's keep the data sheet. I'm just going to move it over here back into my other window. Okay. I'm not going to make you watch me build a voltage divider. All I'm going to do, and I'll explain it in the next stream, is literally take the battery off the voltage. It's time to stop the stream when you start talking like that. Take the voltage off the battery pin like I was showing. Again, right here. Take that out to a breadboard. I've got just a little, in fact, let's just stand by. I'll show you exactly what we're going to do. Just something like this. This already has a bunch of components on it, but just a little breadboard like this. I'll do the voltage divider here, and then I'll branch off of here back over to one of my analog pins that I broke out on my header here. And I'll just start getting readings, and then I can use this thing to get batteries in, like very quickly get batteries into different charge states. Now with my light on, like this is able to be seen a lot better. Like what happens if I like really crank the light on it? Yeah, you can actually kind of read it when I really light it up. Well, that's cool. But anyway, I can use this to put a battery in different voltages very quickly. I can put one at 4.2 volts, one at 4.1, one at 4, 3.9, 3.7, 3.8, 3.87654, all the way down to discharged, and then just plug them in one at a time and see what the ADC says as it's reading that. And that's a simple way to test that. And if we could do that, great. Okay, the last hardware change. I just want to mention it. We'll do it we're not going to do it today. We'll do it in the next stream. That I had down that I wanted to do was this. Let me just show you really quick before we end the stream. Down here. So this section of the board, right? You cannot see that. So let's fix that first of all. Right here. Let me zoom out on it. So here's the board. Again, this is the watermark 12D down here. Oh, there we go, right here. We're going down in this corner. I'll just zoom it in like that. And then I'm going to switch the view here. Again, you're looking at it. Here's that 12D. I think I said watermark. It's silk screen. And so what we're doing is we're looking at this area of the board right here. And so this is the PMIC that we've been talking about a lot. And so if we switch our view back, that's this guy right here, this 17 ground. And so right here, You can see R3, R4, R2, and R1 are really close to where the standoff comes through. And what happens is we have a little bit of the standoff support structure that comes right through like R2, R3. And when it's flipped upside down, these can actually hit that. And so what I would like to do is move these so that they're not right there. I'll probably slide R4 over to here. I'll probably slide R3 over as well, and then just run the trace through here. The trace is fine to run through here. I just don't want the physical resistor running through here. And then with R1 and R2, you know what? I can probably flip these. These are ground, so ground runs all through these here parts. So like I can probably just rotate this left 90 degrees and snug them up here to TH1, which is the thermistor. And then we'll be all clear through here. I think that's what we'll do. We'll do that next time. I'll show you how to do that. It sucks at this point to make any changes because you have to reroute. And so we'll have to delete these. And something I'm noticing, look at this. What is going on right here? That is, I overshot this. Let's select that. Where is that coming from? Right there, look at that. Well, let's just get rid of that. We don't need that. All right, we fixed something. We fixed something before we ended the stream. Okay, that's going to do it. That's long. It was an hour and 6 minutes. That's not too bad. An hour and 6 minutes. I appreciate anybody that dropped in or anybody that watches this after the fact. I hope, again, the whole purpose of this is just sharing my journey. I'm just sharing, building this Internet of Things product with the ESP32 and all the things that I'm learning, just sharing live with you as we go through that process, and hopefully other people can find some value in that. And so I appreciate everybody watching. I hope everybody has an amazing week and weekend for me, and we'll see you back here early next week. Everybody, pick up where we left off last time. Watch last video. We were talking about choosing value around our project 374 RG. And I dug in, looked at a bunch of, got those all sorted out for which resistors what, and I actually started working on